So today, what we're talking about is when the anthropic interpretability team and section 7.6 of Watanabe's book had a baby, and that baby we call TMS1. That's our paper. So Zhongtian, Edmund, Jake, Susan, and myself wrote this paper. Its title is Dynamical versus Bayesian Phase Transitions in a Toy Model of Superposition, and it's on the archive. And what I want to do today is sort of go through mostly the figures in the paper and explain what's going on in the paper, and hopefully that takes not too much more than 30 minutes, and then answer all your questions about the trickiest and hardest bits that you can think of to ask about. So I'll start by talking about briefly section 7.6 and the sort of story of how we came to care about Anthropic's toy model of superposition. I'll talk about phase transitions of the two different kinds that we study in the paper, and then I'll get into the figures, and that's going to organize the time we're going to spend together today. Okay, you can see on the right-hand board here, if I zoom back in, figure 7.6 from section 7.6 of the Grey Book, Algebraic Geometry and Statistical Learning Theory by Watanabe. It gives a picture of a learning curve. This is the Bayes generalization error, BGN as a function of n is the number of samples, and you see this characteristic step-like structure. We never managed to see this even in toy model of superposition, but we set out, we've been thinking about phase transitions in the Bayesian posterior for years now, probably at least 3 years. Section 7.6 is, I think, the first place it's talked about, at least in Watanabe's work. I'll say a bit about the history of phase transitions sort of outside of Watanabe's work a bit later. But we read 7.6, it seemed very interesting, potentially relevant to deep learning, but it's phrased there in the context of one hidden layer tanh networks, and we never actually managed to make that work. Well, Edmund was the one who suffered through that, but with quite a lot of effort, we didn't manage to see sort of convincing phase transitions there. And we sort of thought about it off and on for a while, and eventually, partly because we looked at the toy model of superposition in this seminar, started looking at it in connection with this topic. And it turns out to be really kind of embarrassingly good as a toy model, not only of superposition, but of what we call Bayesian phase transitions. So I'll say a bit about what a Bayesian phase transition is. This is going to be pretty heuristic, what I'm going to say in this talk, because the details are in the paper, and many of these issues we've touched on in the past, so I don't feel the need to be particularly precise. So if you have a statistical model, px given w, trying to model a true distribution q of x, you have a parameter space, capital W. The Bayesian posterior, given some samples dn from the true distribution, is some distribution, probability distribution over the space of parameters, and it depends on the sample, and in particular depends on n. And if, for some small change in n, the posterior changes markedly in terms of where it's concentrated, that's an example of what we call a Bayesian phase transition in n, the number of samples. It's not the only kind of phase transition that might be meaningfully called a Bayesian phase transition. Indeed, phase transitions with respect to hyperparameters are much more extensively studied, not only in Watanabe's work. Liam Carroll's thesis is on that topic, but it's also, as maybe Rowan could explain better than I can, quite extensively studied in the context of Bayesian inference in the presence of noise, as you vary the amount of noise, and many other hyperparameters, sort of in connection with statistical physics. So this story of phase transitions in Bayesian inference as a function of changes in the true distribution or other hyperparameters is relatively well studied. I wouldn't say settled or anything, but I would say, as far as I can tell in comparison, the kind of phase transition that Watanabe is studying in section 7.6 is sort of like essentially unstudied. Section 7.6 of the Grey Book, section 9.5 of the Green Book talks about the discovery process. Well, I guess I've said what a Bayesian phase transition in N is. I haven't connected it to this picture. So let me see. Green, blue. Explanation complete. This figure, I think this community has seen this figure and this story many times, so I don't feel obliged to explain it again, but figure 9.3 maybe is a little bit more esoteric from the point of view of this seminar anyway. So this is where Watanabe in the Green Book, so this is figure 9.3, Green Book, Mathematical Theory of Bayesian Statistics, talks about the discovery process, K components. You could think of this as being the number of weights that are used if you have a one hidden layer network, so it corresponds sort of like inversely proportional to the sort of complexity of the singularity on the left-hand board. So I'm not sure I want to say too much about this figure, except to say that in this section of the Green Book, Watanabe studies it's a Gaussian mixture model, I think. I hope that's Edmund's thumbs up. So I think that's correct. So he studies, yes, thanks Edmund. So he studies a mixture model and shows there's a phase transition in N there. And that, as far as I know, is those two examples, section 7.6 and that mixture model. Section 7.6 doesn't have any experimental data. It's just a purely theoretical study and somewhat sketchy in that it's sort of really the most speculative, least mathematically tight part of that book, which is otherwise very solid. The Green Book, this treatment in this section is quite serious, and there's another section on phase transitions that talks about transitions in hyperparameters of the truth, which is solid. This part is more heuristic, and there's some experimental data. But that together, I think, amounts to the complete story of how Watanabe has treated phase transitions in N. There's another talk, which we're citing in the paper, which is sort of an elaboration of what he's saying in section 7.6 of the Grey Book. But that's sort of, as far as I know, where the situation stood in terms of phase transitions in N in singular learning theory. We were looking at it. There's various theoretical issues that are quite interesting and potentially quite deep and difficult, because this story necessarily involves unrealizability and various other frontier issues in the theory. Most of those remain open, all of them. We haven't really resolved any of the theoretical issues, apart from some minor things. But the thing that we were really stuck on, I believe, was finding a toy system with a rich phase structure and lots of transitions that we could just play with and really figure out what was plausible and implausible, or whether the whole story even made sense at all, in terms of the theory is fine, but does this actually happen in practice? At some tractable scale in parameter count and number of samples. And that's what the toy model of superposition did for us, and why we're so happy with it. Okay, so I think that covers phase transitions in N briefly. I want to talk about dynamical transitions in a moment, but first I'll pause for questions about that sort of historical overview. So dynamical transitions. Phase transitions in N can be given a precise mathematical definition. I didn't give it here. We're not really giving it anywhere. It's maybe a little delicate. But transitions in training time is sort of even more difficult to be precise about. We're calling a dynamical transition. Well, in the paper we say it's something like you observe a trajectory over the optimization moving from a neighborhood of one critical point of the loss to some other critical point, sort of dominated by plateaus in the cases where it's near the critical point. That's reasonable in the context of TMS. It is actually what we observe in the training trajectories. But if we're talking about dynamical transitions, or what people in deep learning papers would call phase transitions that they observe over training, like the idea that it's only ever well described by plateau, drop, plateau is not accurate, because the loss often won't reveal that kind of structure at scale. So if you click on the left-hand board here, this is from the Anthropics paper, the toy model of superpositions, also a paper/blog post from Anthropic. That's El Haj et al. This is the in-context learning and induction heads paper. You can see on the top here, loss curves. This is training a particular transformer model. If you just pay attention to the 2-layer loss plots, 2 or 3 layer, this part marked in orange is meant to be a dynamical transition in the language I'm using here. You could kind of say it's a bit like a plateau beforehand, maybe, and there's sort of a bit of a plateau after, but it's a bit of a stretch. It's not a plateau. It's just kind of like some bump or something in the loss. However, there are other metrics with respect to which you can have a picture that looks like a plateau separated by 2 plateaus separated by a drop. So I want to be careful to just be clear that while in the domain of TMS, when we're comparing Bayesian and dynamical phase transitions, we're adopting a particular definition of dynamical transitions for clarity and attempt at mathematical precision. But the term is meant to sort of denote a whole range of transition-like things that might happen over training, which might not be visible as plateaus separated by drops in the loss, but would be perhaps more visible in terms of sudden changes in structure or other metrics like the in-context learning score here. But in this talk, I'm going to have that precise, more narrow meaning in mind. All good? Okay. So Bayesian phase transitions are sort of not well studied, mostly because I think you need singular learning theory to really talk about them. But this kind of transition, something jumping or changing suddenly over training, have been noticed for decades, going back to the 90s. Matt pointed out a nice paper to me about this. It's sort of come back in a big way recently, because people observe transitions that sort of actually matter, in the sense that the structure that emerges in them seems important. So induction heads would be a good example. But like, that's not that mysterious, dynamical transitions, right? So it's in the context of nonlinear dynamics or catastrophe theory. That's not that surprising that you would have some sort of structural change like that at a point that's relatively localized in time and also in parameter space. The picture on the right here is from Gilmore's book on catastrophe theory, and it's exhibiting a kind of generic expectation of systems with isolated critical points that trajectories will sort of have their overall structure dominated by those critical points. Refers to that as the crowbar principle. And there's more extensive detailed work in training dynamics going back to Amari and his school in the 90s, and lots of recent work which we're citing in the related work section of the paper on saddle-to-saddle dynamics that gives you some kind of inkling of how those general principles manifest themselves in particular deep learning systems. Okay, so that could lead you to have the impression that, well, there's some mathematics there and people see dynamical transitions, then this seems like it's probably on track to be understood without singular learning theory. I would argue otherwise. So let me draw a little cartoon here, which gives you a bit of an idea of the problem of the other approaches to studying dynamical transitions in the appearance that are responsible for the appearance of structure in neural networks. So let's say dynamical transitions, Bayesian transitions, learning dynamics, statistical physics, and down here I'm going to put high-level principles. So something like thermodynamics, which is what you want, in the sense that you don't want to be, doing detailed level studies of very large, complicated systems. There's sort of no obvious way to ever make progress with that. Dynamical transitions have mostly been studied by learning dynamics in sort of toy systems where you can write down the equations and make some simplifying assumptions and then study what is going on. Those are cool papers. I'm not trying to criticize them, but it's very unclear how this link is supposed to work. There is no extant principle in mathematics or physics that would get you from a detailed level understanding of that to high-level principles, at least that I'm aware of, that doesn't factor through something like statistical physics. And it's not clear how learning dynamics, as people are doing it, would make some link to statistical physics. On the other hand, Bayesian transitions in SLT have a very clear link to statistical physics, and that in turn has a very clear link to high-level principles. I'm not saying those links exist, but it's very clear how you might go about pursuing them. So there's two question marks there, right? So going from the observed dynamical transitions and trying to understand them to high-level principles, you can either try and go through learning dynamics, or you can try and make a link to Bayesian transitions. And the paper, in part, is about trying to examine this link. Okay, so the paper has two main goals: to be a good toy model of Bayesian transitions in N, and to try and establish this link between dynamical transitions and Bayesian transitions, and some other things besides, but those are two of the things we wanted to do. What am I doing for time? Yeah, any questions? Otherwise we'll move over to the next set of boards. Okay, let's move. I think I'll just add one more bit of context before going through the figures in the paper. That's to say something about, if it's a toy model of superposition, what is superposition? And to describe the model, maybe I'll just start with the math. So the problem we're considering is to map an input x that is in r to the c, and for all the figures I'll show you, c is equal to 6. It's going to map it into some smaller dimension. In all the figures we're going to show you, r is equal to 2, and then try to map it back up to reconstruct the input. Okay, and the way that overall function works is ReLU W TW x plus b where W is a matrix with 2 rows and 6 columns, and B is a bias. And the loss function is how well do you do at reconstructing every x according to some distribution over possible inputs x. The L2 norm is a measure of reconstruction error. In our case, we're studying the high sparsity limit of this problem, which refers to what distribution over x's you take, and so the x's are only sampled along coordinate directions, so there's no linear combinations. That might seem like it's a kind of trivial problem, but it's already extremely rich. The general case where you're not in high sparsity is quite open. So that's a problem. That's what's often called an autoencoder. So it's a one hidden layer ReLU autoencoder. You might notice it's very similar to the system in section 7.6, which is a one hidden layer 10H network. There are some other distinctions, like the position of the ReLU is not the same as in that section 7.6. But morally, maybe they're quite similar systems, and indeed, we'll see a bit later with this somewhat mysterious plot of L against lambda that indeed the phase structure is exactly what Watanabe is saying in section 7.6, which is quite interesting. So somehow we came full circle. We wanted to study this 10H network in 7.6. We despaired and went looking for something else, and we ended up basically studying the same thing, just some slight variation. Okay, so this is the system. Why is this called superposition? Well, it's got to do with this term superposition actually wasn't invented by Anthropic. Aurora et al. Wrote a paper, let me check when it was, 2018, which Anthropic is citing. The title is Linear Algebraic Structure of Word Senses with Applications to Polysemy. I don't actually know how to pronounce that word. So the point of that paper was just to notice that if you have word embedding models like word to vec, that, or you just take the embeddings of these days a transformer model like a GPT that represent words as vectors, words that have multiple meanings, the example they use is tie, T-I-E, you might expect that those multiple meanings are sort of hidden somehow in that word representation, right? What they say is something like the embedding for the word tie, you might expect it's a linear combination of vectors. So this is the tie that you put around your neck, and this is the tie that you do like a draw in a sport match. And these multiple senses, and maybe there's many more, maybe these multiple senses aren't actually linearly independent. There's some directions in that vector space, and so v tie is, those aren't the coefficients in a basis, alpha 1, alpha 2, but something more like an over-complete basis, which is a topic that's come up quite a bit in mathematics and applied mathematics, in connection with compressed sensing and sparse coding and so on. And so this idea was explored in Aurora et al., including actually, I think, the dictionary learning thing that Anthropic sort of ended up doing, although not exactly. So it's, yeah, this paper by Aurora et al. Is sort of quite important, I would say, in the history of this superposition idea. Why superposition? Well, that's just what it's a fancy word for linear combination, essentially. In physics, it has a specific meaning, but here it just sort of means linear combination. Okay, so let me get into the figures. Are there any questions about the setup?
Is it very important to have biases? I understand they've caused a lot of complexity in the analysis because there are different critical points that just differ from their biases.
Yeah, that's right. You mean important for like what would happen without the biases? Would it actually achieve the same? I'm not sure what you mean.
Yeah, that's what I mean. Like, could you see a plot like this if you didn't have the biases? A plot like the step plot.
You'd still see this without the biases. It would just be harder to find in a way. Like the training process is less behaves less
Okay.
well without the biases.
Okay.
Yeah, so we did spend some time with the bias-free case. Obviously, theoretically, it's easier. Well, in some respects, it's theoretically easier. Zhongtian definitely was happier when we switched to thinking about the case with biases for many parts of the analysis, if I remember correctly. So there's trade-offs there where it's simpler, but
Okay.
like some of the critical points actually, I mean, it's worth pointing out that this function L is not analytic, right? So there's a ReLU there. There are points in the parameter space where it isn't differentiable. And without the biases, many of the critical points you actually care about land up on those points of non-analyticity or boundaries of various kinds of things.
Okay.
Yeah. So that's one way in which it improves with biases. Yeah. Okay, so in their original paper with Anthropic's original paper, they noticed some plots like this where over training time you have these sort of steps and decreases in the loss. They didn't spend a lot of time on this. Mostly the phase transitions that Anthropic was interested in happen when you vary the sparsity and look at what happens at the end of training for different values of the sparsity. I think there's one plot looking at behavior over maybe two sort of different views, looking at what happens over the course of training time. So that piqued our interest, and we went looking and sort of reproduced that pattern, which you can see in the blue curve on the left. But what we're showing here on this plot, in addition to that, is the learning coefficient, or local learning coefficient estimate lambda hat, which you can see increasing in a stepwise fashion. And this sort of is a reflection of what I was showing in that figure 7.6 in the dynamical setting. So figure 7.6, remember, we're saying that you have phase transitions as you increase the number of samples from higher loss solutions or regions of parameter space that are more complex, so lower learning coefficient, to regions of parameter space that have lower loss but are more complex. And you can see that very clearly here, although at this moment I'm sort of conflating the x-axis, which is time, with the number of samples, which is actually the main question, right, of how are those two things related. But broadly speaking, there's kind of like some conceptual similarity between the learning process as you increase n and what seems to be the learning process of SGD as you take more steps. I don't want to oversell the degree to which we understand that connection, but at some higher level, that's sort of similar. So you can see here, visualize the three different critical points that these plateaus are nearby. Two foregons. Foregons, we call them because 4 of the input features in R to the C, so 4 of the basis elements, when you look at their image here, so E1, E2, E3, E4, you look at their image there, by which I mean you apply W, right? So this WX over here, you apply W to the first 4, or just any 4 unit vectors. You get 4 vectors in R2. Those are the columns of W, of course. And if you plot those columns in 2 dimensions, you get the kind of pictures you see on the left, or at least you get the parts that radiate out from the center on the left. The parts that actually make up the square are not part of the data. They're added for visualization purposes. I don't think we need to get into exactly what they're there for, but the columns of W are visualized by the things that radiate from the origin. So we say a k-gon is, roughly speaking, when there are k columns that are non-zero. So this is foregone to foregone to 5-gon, and there's 2 different kinds of foregons, which is, I guess where part of the entertaining aspect of the paper comes from. Many more different kinds of foregons than you might imagine, and I'll say something about that a bit later. Yeah, any questions about this? Is figure 1 from the paper. I'm going to move through the figures in order. Any further detail on this that I can give you? Okay, so these are perhaps the main takeaway from the paper. So the right-hand side here shows you a visualization of the Bayesian posterior as a function of n. So what do I mean by visualizing the Bayesian posterior? Well, the Bayesian posterior is a distribution over parameter space. Parameter space is a compact subset of this space, right? Because a parameter is a pair consisting of a matrix and a bias. And we're visualizing in the pictures that I just showed you both the columns in the sort of picture, but below that in the plot also the bias. So if you divide up parameter space into, you partition it in a certain way so that here are 4 gons, here are what we call 4 plus gons, here are 5 gons, here are 6 gons. Not saying yet what 4 or 4 plus gons or 5 plus gons exactly are, but some particular kind of critical point. And then what you can do is you can sample from the posterior by some method, and then you can just count how many of those samples end up inside the foregon phase, in this case 2 out of however many dots I made, 3, 3, 3, 9. So that gives you an estimate for the occupancy of that phase, and that's what the y-axis here is, that fraction. And that fraction changes as n changes. So for each n, you sample some number of samples from the posterior, and then you plot for each of the phases the occupancy. Now there's many details here as to like whether you think this picture really represents what the true Bayesian posterior is doing, and we'll get into that, but I want to give you the high-level story first. So what you see here is, I guess the first thing to say is that the smaller n is, the harder, well, there's sort of 2 ways this is hard. For large n, various things go wrong. So danger, and for small n, things go wrong. I don't know exactly where to draw the danger zone, Edmund. I forget, like 400, 300, somewhere.
Conservatively, 400.
Yeah, okay. So somewhere below there, we stop trusting the MCMC estimates to like actually be an accurate reflection of what the posterior is. We'll go into what that confidence or lack of confidence is based on later on.
Sorry,
Yep.
let me correct that sentence. I think MCMC is doing well in those low ends. It's the classification that is not doing well.
Oh, that's right. Yeah, thanks. So up here, MCMC fails. We'll show the precise sense in which it fails later. Down here, MCMC is probably okay, but the classification scheme we have for dividing up parameter space starts to sort of break. We can go into more detail about that if you're interested. But for some range between roughly somewhere starting between 300 and 400 and up to the end of this plot roughly, we have some reason to be confident that MCMC is giving a good picture of what the posterior is doing. And the dramatic feature you can see here is that for low n, the 5-gon phase is dominating, meaning that when you sample from the posterior, mostly what you get are WB combinations that are not only have 5 non-zero columns, but actually are 5-gons in a precise sense. So the 5-gon is some particular class of parameters which are critical points of the loss, and we know exactly what that is, and the samples are like that. And as n increases, the trade-off becomes around the other way vis-a-vis the 6-gon, so that at high n, most of the samples look like 6-gons. And this illustrates the basic sort of principle of phase transitions in Bayesian statistics as exhibited by singular learning theory, which is that, at a qualitative level, for low n, it's possible for bad parameters from the point of view of being close to the model, with that parameter being close to the true distribution, or as we would say in ML, the loss being low. So the 5-gon does not have the lowest possible loss, but it is simpler than the 6-gon, and therefore it's possible for it to be preferred by the Bayesian posterior for low n. But as n increases, the emphasis on low loss increases, and so the 6-gon is preferred. And this basic story of how phase transitions in the posterior should happen is being exhibited here very clearly by the MCMC samples. Okay, so that's a qualitative story, so that picture is consistent with what we would expect from SLT, but it's more than just a qualitative match. So if you look on the left-hand side, you'll see the theory plots for the same phases. And these theory plots are based on theoretical values of the free energy. So the free energy of some phase we're approximating by the free energy formula, where the terms of log n and lower are just swallowed into some term that's treated as essentially constant. And I won't say much about that unless you ask me to. It doesn't matter too much for the 5-gon to 6-gon transition, and so I think it's not too important from the first pass. So theoretically we can compute this because we can find the critical points that we think should be responsible for the phase. So in each of these regions there's some special point which you could call W alpha star. That is a critical point which we identify as being in that region, and we hypothesize it dominates the Bayesian posterior, and then we go look at samples, and indeed it is the case. And you take its loss value, that's L alpha, and in some cases, so 5, 5 plus, and 6, we can theoretically derive the learning coefficient due to some hard work by John Tien understanding the loss in local coordinates. So we theoretically compute the integral that I put on the board earlier to give explicit form for the loss function, and then look at it in local coordinates and find it's minimally singular and use that to compute a theoretical value of the loss of the local learning coefficient, lambda alpha. That gives us a theoretical free energy, and then if you plot those free energies for those alphas as a function of n, you get this distribution, and you see it visualized in this plot. For the 4 and 4 plus, what we use are estimated values of the local learning coefficient, not theoretical values. For the purposes of the headline result, which is the 5 to 6 transition, it's sort of irrelevant, right? I mean, the 4 to 4 plus are over here. Even if the values for the learning coefficient, the L alpha there is theoretically known, but the learning coefficient is estimated, but it's sort of irrelevant to matching the 5 to 6-gon transition, so I don't want to worry about it right now. And what the theory predicts is indeed a 5 to 6 transition. It's at almost exactly 600, n equals 600. The MCMC crossing, I mean, it's impossible to get a very high resolution on that number, but it's clear that 600 is consistent with the experimental result. So this is, the part of the paper we're very happy with, I guess. One of the parts we're very happy with. So the upshot from that is that phase transitions in N happen. We knew that from the Green Book, for example, right? But this is another example of it happening, and in a system that, I guess, not that mixture models are not of practical interest, but in another system that people have encountered naturally, this toy model of superposition, we see this happen. And the free energy formula accurately describes what's going on in that transition. So that's figure 2. Any questions?
So there are some differences between what the free energy formula is going to predict and this, like the crossover point being slightly earlier in the prediction between the 5 and the 6, and also the proportions, like that green curve in theory goes down really low, really close to 0 by like 1,000, and it's not there. It's not all the way at 0. So there's like a approximation error with your MCMC, and there's like there's also lower order terms, right?
Edmund mentioned
what other sources of
classification
error
error.
might there be?
Yeah, I
Yes,
think,
classification. Yep.
yeah, that it's. I mean, phases. Yeah, it's tricky. I guess we could list 3 or 4 things that are tricky about making this MCMC plot. I'm not sure. Yeah, so maybe the first thing to say is that 5 gone, 6 gone, and so on, they're points, right? But in order to estimate occupancy and draw these proportions, you have to draw a region in parameter space. And that's not like a canonical thing, right?
Okay.
So you have to come up with some notion of, well, this particular thing I'm looking at is counts as a 5 gone and not as a 5 plus gone or whatever. And in some cases, maybe that's clear, but it's sort of this is when n becomes small, where things start to fall apart, because it sort of becomes unclear what you should really count a given sample as, and therefore these curves start to not quite make sense. I mean, in the case where you're at a value of n where all the samples look like a 5 gone or a 6 gone, it's very clear that you're capturing the right thing. Does that make sense? Edmund, did you want to comment?
Yeah, I understand the classification accuracy. The classification, might not be capturing things. I'm interested a little bit more in what you have to say about the region, like how close we are to a phase, like classifying the phases. What in the theoretical version, what are the proportions based on there? Like, is there some threshold for being close to these points?
Oh, in the theory, it's just the free energy formula, which is asymptotic. So, so I mean, it's simply what's on the board there. So the z is the sum over all alphas of this quantity. So there's no need to draw or to have a notion of classification, because you're just making use of the asymptotic formula associated to that particular critical point.
So, hold on. Should that be e to the negative?
Oh, thank you. Yeah.
Yeah. Okay. So this is just the free energy put into the Gibbs distribution. So this is the the proportions here are like the Gibbs distribution over phases.
Mm-hmm. That's right.
But
so
why does that predict how close things will be? How close the MCMC samples will be to those things?
Yeah, so in the limit where n is very large, so that the only samples you ever see from the posterior are just really close to some optimal parameter,
Okay.
then there is no need to talk about regions of parameter space because somehow the
Yeah.
samples just all live very close to a point.
Yeah.
So we're considering some intermediate region here where, on the right-hand board, if at a given value of n, you only ever saw samples that were very close to the Platonic 4 plus, 5 plus, 4 and 6, then it wouldn't really matter where you draw the boundaries of the regions, right? Because you almost never see samples near the boundary. It's just very clear, like the samples are 5 or they're 6, and the where you draw the boundaries is irrelevant. So that's kind of the limit in which, when we say there's a problem with classification, it's like if your classification ever, like the details ever become relevant, then you start to worry or something like that, right? So in the left-hand board is describing the asymptotic, where the classification boundary is not present on the left-hand side. So you would only expect good agreement with the right-hand side if similarly it doesn't really matter.
Yeah. Okay, that's clear. Thanks. Summarize something like differences between these plots arising from the fact that the free energy formula is asymptotic, whereas we're considering it finite n cases where the actual formula that is describing what's going on might be slightly different from the free energy formula at low n. There's also it's unclear exactly how to classify points as near a phase, and this particular classification that you're using might be giving nonsensible results, especially at small n. MCMC is also a finite sample-based approximation of the posterior, and there are also these lower order terms.
That's right.
That would summarize sources of differences between these.
Yeah, there's another source which is that we never claim that we find every possible phase or more precisely every possible critical points. We are fairly confident that we did that, but we never claimed that. But in the context of this particular plot, you will see that in the
Other.
On the right, there's an other, and those are just sort of things that we're not that are sort of too close to the boundary or things like that, and you will see that the other sort of decays away as n increases. Also, that's also an effect in the left-hand board as well, which is like that's not all the critical points that we know as either. So the formula sort of for analysis between the transition between two dominant phase, that is not very relevant. But if you go into what is the proportion at which they cross over, that calculation will factor in.
There's another plot that we have in the appendix that's over behind us a bit, and we'll get to later, which shows if you incorporate all the 4 different foregons, it does sort of make the qualitative agreement between these look a bit better. Like you were referring to earlier, that the maximum for the 5-gon phase looks like it's very close to 1 on the left-hand theory plot, but not much above 0.6 on the right-hand side. That's partly due to not accounting for all the other potential k-gons on the left-hand side at that range of ends.
Thank you very much.
Yep.
Yeah, I think it's worth pointing out that this quite gigantic list of potential source of error is perhaps what's fortuitous in TMS, that like every one of them doesn't matter at some for the range for observing that 5 to 6 gon transitions, and even in low ends here, if you go inside and look at those samples and whether or not they are foregons and things like that, they are not like completely. You could still say something like even at low ends, the fact that the green 5-gon curve is high proportion, that is correct. That is true if you just look at the samples. So in other systems, you might need to sort of battle every one of these issues separately.
It's I mean, the reason that you're sort of quite interested in an experimental view on this is that it's just based on the mathematics. Nothing guarantees that any of this really quite makes sense, right? You're using an asymptotic formula in n to compare different phases at finite n. Like, who's to say the asymptotic is a good enough description at that level of n for you to ever see phase transitions in this sense? So it's, I mean, one might be able to make theoretical progress on that, but the reason we were so keen to find an experimental domain in which to study this is that a lot of these basic questions are very hard to settle based on pure theory alone. So it's quite heartening to see that even at n as small as, I think we're increasingly confident that even for quite small n, even below 600, it's not crazy to imagine using the free energy formula. So that's nice. Okay, I want to move on to talk about dynamical transitions, but on the left-hand board, I won't say much about it, but you can see a T-SNE version of the phase transition where as n increases, you see the 6 gons, the red dots, dominate in the samples over the 5 gons, the green dots. So that's sort of another way of seeing the same thing happen. Okay, so dynamical transitions, this means training by SGD, initializing in some particular way. I'll get to in a moment. You run training runs and then you see, well, you plot the loss. So how many trajectories was this, Edmund? 400, I think, from memory. So there's 400 SGD trajectories here running for the same number of steps. At some interval, you take the weight, you compute the loss at that point, and you compute a local learning coefficient, and then you plot that point on the left-hand side with a color given by the learning coefficient. Negative 10 is a valid learning coefficient. Not really, but there's better values of the local learning coefficient in the final page of the paper, but it's I think accurate not to worry too much about the negative numbers here. Just rescale them somewhere up to between 0 and 1, perhaps. The thing to take away from this plot is that the claim that I made earlier about trajectories being dominated by critical points is, you can see this in the image. That's the plateaus. The trajectories all end on sort of stabilize on plateaus. Moreover, the plateaus are at loss values which we've theoretically computed for critical points that we classified. You can see a lot of different 4 gons, 5 gons, and 6 gons. So this is the basis of our assertion that, at least for this initial distribution, we understand where trajectories end up. The initial distribution is somewhat strangely, but it takes a minute to explain why it makes sense. We take samples from the Bayesian posterior as the initial distribution at n equals 100, Edmund?
Yes, just the lowest one we have access to.
Yeah, that's right. Mostly that's just so we know it's going to end up in sort of
close to knowing critical points.
I think it's if you start too low down the energy scale, you're never going to see these 4 gons higher up the energy scale. So there's sort of like a balance between where you initialize the trajectories in order that you see like a diversity of endpoints. And if you just kind of randomly initialize with like a normal distribution near the origin, you might end up only seeing 5 or 6 gons, for example, if I remember correctly. So this choice of initial distribution is kind of made to increase the diversity, or to sort of reflect the diversity of critical points that exists. Okay.
A question.
Yeah.
So have you checked that the plateaus that you end up on are well described as these critical points, because this looks like you're just sort of saying that the
energy levels are the same.
The energy levels and the lambda hats line up because the colors are kind of matching what you would expect.
Yeah.
As well.
We know beyond that it's not just match on the level of the energy. So if you look at the actual trajectories, they are indeed the things we call these k-gons.
Cool.
Okay, so dynamical transitions, meaning trajectories dominated by critical points and moving between them. The transitions themselves are visible on this plot on the left as some of these curves that move between two different levels. So you can see some here, 5 to 5 plus. You can see some here.
There's a couple of very sparse, like those dots between.
Some of these.
Places. Yeah.
This is not the best plot to read off transitions from. So for that, there are other figures that show you actual individual training trajectories, like the one that I showed you at the beginning. But quite a few of them, we generated many of them and looked through them all for all the transitions that we could find, and those are listed or summarized on the right-hand board here. The individual figures you can find in the paper, or I think they're around here somewhere. But this is in summary form a rather interesting and somewhat mysterious plot. So the x-axis here is the estimated local learning coefficient. The y-axis is the theoretical loss. The points are the different foregons, these critical points that we classified, which are described by this other plot as being the endpoints of trajectories. Red lines going down and to the right are the observed transitions. We're not claiming those are the only transitions that ever happen because, well, how are we to know the next time we run it we don't see something else? But these are all the transitions, not only, the runs that I did and Edmund's 400. I believe it's accurate to say these are the ones that appear in those samples. Okay, so what do we see? Well, it's quite amusing. First of all, the lines do go down and to the right. So the fact that they go down is obvious, right? That's you're going from a value of the loss to a lower value of the loss over time, SUD steps. So of course that's expected. The fact that they go to the right corresponds to this kind of behavior of the local learning coefficient, right? So this picture is an indication of this stepwise behavior, or at least the sort of opposing directions, decreasing loss, increasing lambda hat in dynamical transitions, which we understand is a basic feature of Bayesian transitions. The fact that as you kind of go along these curves, the increase in lambda hat is greater, right? The fact that it is kind of this shape is a further fact. So what's this saying? It's saying that the slope of these lines sort of increases. That's a negative slope, right? So it's going from large and negative to small and negative. So it's increasing along sequences of transitions, or if you like, as lambda increases. We don't quite understand. That's consistent with a sort of Bayesian story. I think we're not super confident on this part yet, but it's quite tantalizing, this curve. Partly because this is exactly the phase structure that Watanabe was sort of pitching in section 7.6, perhaps with the basis of literature, but perhaps not completely. So it's rather interesting to see it show up here. Yeah, let me see if there's anything more I want to say about this. I think the main takeaway from this is simply that all the dynamical transitions we observe do increase lambda hat. I think that's the main takeaway, and then there's sort of like some interesting speculation about the structure of this diagram, which remains to be understood. Okay, I do want to wrap up in about 5 minutes, but there's time for questions about this slide.
I think I might have missed. What are the red lines?
Those, yeah, I should have explained better. So you see here, there's a red line from 4 plus to 5. That means that a transition, a dynamical transition, was observed between these two critical points. So in our distribution of SGD trajectories, at some point we saw that there was a trajectory that went from 4 plus, was in a plateau near a 4 plus gon, and then afterwards was in a plateau near a 5 gon.
Okay, whereas you never actually observed a 4 plus plus minus to 4 transition.
Correct, yeah. This never happened, yeah.
And so it's like some kind of connectivity of like neighboring phases or something like that, or do you think that the phase transitions that are like without a red line, like that one that we just drew, are they in principle possible and you just didn't happen to see them, or do you think there's some reason why they're not really possible?
I think there's some reason they're not possible, but it's not clear it has an explanation. It's not a fact of SLT. I don't think it's a thermodynamic fact. So as far as, well, at least not on the level of just these quantities that are on the page. So this line does increase lambda hat and decrease the loss. From a free energy point of view, it would decrease the free energy. It's allowed. But like in chemistry, not every reaction that is allowed actually happens. And in this case, we don't understand it, but there's, well, it seems to be that the transitions sort of annihilate a plus and a minus.
Okay.
So 4 plus plus minus can go to 4 plus, but it can't go to 4. And that's
interesting.
If we understood it, would probably seem to be a fact about the loss function and the loss landscape that is purely dynamical or to do with symmetries or something, and it's not reflected just in a pure free energy calculation. There's just no path in the loss landscape that goes that way.
Yeah. I mean, an abstract like example I have in my head is something like, well, you want to make your way away from the 4 plus plus minus. There's like a 4 plus that is you would hit first before you travel to any 4. And so why would you go to the 4? Because the 4 plus is then slightly better.
That's right.
Well, and there's a big error bar there, but maybe it's better.
The error bar is in the learning coefficient, so the loss is definitely lower than the 4. So you're not going to SGD is never going to go up. Yeah. Any other questions? All right, let's move over to the next. Oh, go ahead.
Yeah, so this is something I sort of asked Edmund, I think, but I kind of wanted to get your take on. But it's sort of, you see in that left plot that the phase transitions seem to be kind of infrequent, I guess, and sort of the hypothesis is that in real systems they're not only not infrequent but so frequent that you kind of they're everywhere. So I guess what kind of ideas do you have as to sort of what the gap there might be?
Yeah, I think the transitions aren't infrequent at the beginning, right? So I would say this is a kind of, if you look at the right-hand plot, I think it makes sense that, like, over here, transitions are easy. Because if you look at this hyperbola, when the learning coefficient is small, each transition, I mean, it's you sort of only have to, like, the addition of structure is rather small, but you decrease the energy a lot. So it's sort of relatively easy to make the transitions, and that's sort of like a low-end phenomenon, high-temperature phenomenon, right? It's very easy to make progress from these very, very degenerate, bad solutions. I mean, John Tian hates it when I say this, but like 4 minus is kind of like a 3 gon, and 4 minus minus is kind of like a 2 gon. Not exactly, those are different things, but like in some level, maybe it's not completely illegal to think that way. So they're just really bad solutions. And so making progress there is relatively easy, whereas down here, sort of, I mean, you look at the 5 to 5 plus, right? It's sort of, you only decrease the loss by a relatively small amount, but you have to add a lot of structure, right? So I think this is just harder. And so I think that's what explains this picture, at least that's my running theory, low confidence, but that's how I think about it. So to compare this to, I mean, there's many things that are nice about TMS, but there are many things that are artificial too. It's a very, very small system, right? So it's sort of heavily constrained in some ways, and I think the fact that phase transitions, you already see that if you increase C, the number of columns, make it like 20 or 30, there's more transitions and they start being harder to spot. And yeah, so I think that's a kind of artifact of the size of the system. Yeah. Okay, let's move on to the next set of boards. But it's sort of interesting to note that as that curve goes up, you start cramming lots and lots of different k-gons into the sort of space of low learning coefficient, right? It's kind of like a visual indication that you're going to get things that are much more degenerate than minimally singular, and that's also our running hypothesis. Okay, so those are the headline results of the paper, right? That Bayesian phase transitions exist. We see them in TMS. The theory does a pretty good job of talking about them. Dynamical transitions exist there. They are between the critical points that the phases of the Bayesian posterior is also talking about. And the transitions that we actually see are consistent with the free energy formula in the sense that the dynamical transitions decrease the free energy. So again, to use the chemistry analogy, you use the free energy in chemistry to say whether a reaction is sort of could spontaneously happen or is ruled out by thermodynamics. Just because a reaction is allowed in the sense that it decreases the Gibbs free energy doesn't mean it must happen. There could be some other reason why it doesn't happen, but it's at least like that obstruction doesn't prevent it. And at the moment we think about the relationship between the Bayesian phase transitions and the dynamical ones in that sense. So if the dynamical phase transition, like the question we have right now, we term this as the Bayesian antecedent hypothesis, is do the dynamical transitions we see, are they like consistent with the free energy formula in the sense that they decrease the free energy? Or to phrase it differently, is it possible for there to be a Bayesian phase transition between these two phases at some value of n? And that so far is consistent with what we see experimentally. But this is left at the level of a kind of question mark. We do not understand the relationship between Bayesian and dynamical phase transitions as a result of this one system, but we're sort of at least it's the existence of a relationship between these two sets of things, the sort of most natural proposal for a relationship does seem to hold up so far, and we look forward to examining it in in larger and more complex systems. So those are the headline results, but I think for this community, one of the big things you want to learn from this paper is how to do all these things systematically and carefully. And so there's a bunch of so the methodological progress is I guess what I'm saying is maybe among the most important pieces of progress to come out of this paper. So what you're seeing here are some of the MCMC plots, sort of health plots. There's the range of things like this that Edmund has come up with. This is what gives us the confidence to say that MCMC plot is not a delusion. Given the time, maybe maybe you can just explain one of these, Edmund. I don't know whether 300, 1000 or the bad one. If you could give like a 5-minute description of what this is about, that would be great.
Yeah, can you put the second and third?
Sorry?
Sure.
The good and bad, yeah.
Yeah, good and bad. So I think so for people who run MCMC for a living, maybe trace plot is like health diagnostic. Diagnostic is important. This is one kind. If you Google trace plots in MCMC, usually people say meant that for like trace of individual coordinates, but there is like 18 of those here, so that's not a good way to do it. And here we are just tracing over the loss. By trace, I mean on the x-axis we plot the index, the number of iteration the MCMC has taken, and on the y-axis is the loss on those. I just stacked all the different chains together horizontally. Okay, so if you look on the right-hand side, so these are sort of health diagnostic. So if they look okay, it doesn't mean that nothing is wrong. But if they are bad, you know something is wrong, and that's what's happened on the right hand board, which is that you see that there are certain chains. For example, that orange chain at the end there, which never explore anywhere else, and then every other chains. Even though there is a possibility to go to where the orange chain will go, but they don't go, which means that the proportion you calculate from these data will be completely determined by where a chain gets stuck. And there is also a particularly so like something happened there. That means that the MCMC algorithm completely gets stuck there. So those are kind of the tumor signal you look for in a MCMC chain, and on the left is kind of a healthy ones. I should also point out that running MCMC in singular model is a very understudied region. So every MCMC paper out there that propose new method and things like that has always have like tests toy MCMC landscape that are regular model. There may be many modes. That's the primary issues. But I think from here, from experience with singular model, there's an additional, having multiple different phases with that kind of competition predicted by the free energy is an additional layer of challenge. Yeah, I think that's all I want to say.
Great, thanks. I think I'll wrap up there so we have time for some research updates. So thank you, everybody. I'm happy to take further questions.